We should sit in silence and pretend we haven't gone live yet. We are live. Welcome to the ASVs November AstroTalk. Whoa, that's a bit reverby there, Lee. Turn the volume. I'll keep going. This month we're changing things up a bit, and instead of a presentation from our guest speaker, well, that's a bit better, isn't it?
Yeah.
We're going to have a more intimate sit down where the guests who are here and those of you at home are going to be able to ask questions. So be sure to pop a question in the chat. I'll see it on one of my many phones. And we're going to have a chat with Steph Bernard about all things astrophysics and James Webb and the universe and beyond. First things first, I just wanted to say another big thank you to everyone for Sea Lake Astrofest. It was one heck of a party. It was good fun. Everyone had blast. The volunteers were great and the attendees enjoyed themselves, and we all got to see, well, most of us, except for a few people who are here tonight, got to see a lovely aurora. That's what happens when you go home early from a viewing night. You miss out on the best part. We do have our Christmas barbecue coming up on December 9th. We also have Mount Buller Star Festival on the weekend of the 6th and 7th of Jan. Buchan Astro Weekend, which is going to be the weekend following the Messier Star Party, as well as the Messier Star Party, which next year is going to be Labor Day long weekend, but in Hamilton, not at Leon Mao Dark Sky sites. We're taking it on the road. The circus is starting to move around now. How cool is that? But before we begin, I'd like to say, in the spirit of reconciliation, the Astronomical Society of Victoria acknowledges the traditional custodians of country throughout Australia and their connection to the land, sea and community. We pay our respect to their elders past and present and extend that respect to all Aboriginal and Torres Strait Islander people today. The ASV loves to bring the streams to you, and we couldn't do it without your support. So if you are not subscribed or following us, please hit the follow on Facebook and subscribe on YouTube so that you can put the bell on so you know when we're going live. But now we're going to get into our talk. Steph Bernard is an astrophysicist who works at the Melbourne Planetarium. What a cool job. As well as lecturing at first, second and third year? Or
Not lecturing, demonstrating and tutoring.
Tutoring.
Yes.
First, second and third year university
masters.
students in astrophysics.
Yes.
At Melbourne University.
Yes.
And her area specialty is galaxies and the early universe and James Webb Space Telescope.
More like Hubble.
Hubble. More like, I should know this. I've known Steffi long enough. It's a bit embarrassing that I don't know this now. How you going?
Yeah, good. I had COVID, which is why I missed the aurora on the weekend. Very, very sad.
You have a fair and legitimate excuse, unlike some others. Well, we'll have you there next year, that's for sure.
Absolutely.
So that'll be good. So we might start a bit about your background.
Yeah, absolutely.
And how you got into astrophysics.
Yeah, I think I was interested in astrophysics from a very young age. My father is here today and can thumbs up, thumbs down if I'm lying. Yes.
Can you just thumbs down when she says the truth anyway?
he's
just
a
to
bit,
stir her up, yes.
bit mischievous. Yeah, so when I was in year 2, I had a little book with the planets, which was, like that thick picture book. I read it cover to cover. It was my show and tell at least once, probably more than once. I wanted to tell all the kids in my class all this stuff about the planets that I was just learning with my newfound reading skills. And yeah, the book literally fell apart. As I got older, I was really interested in science. And I grew up in New South Wales in Newcastle, and so we did a few trips through the country, and one very memorable trip was to Parkes in their radio telescope. And just sort of like walking up the road and you see this enormous dish. And I've got some pictures somewhere of me, mugging with like the, trying to hold it as like an 8-year-old. But they're on film, so I don't know where they've ended up. But we watched a video at the visitor centre there on quasars, which are supermassive black holes at centres of galaxies. And at that point, this was 1997-ish, 8-ish, where still, we didn't know as much as we know now about them. And so I was just amazed that like these things that look like stars were actually black holes, you know, billions of times further away than the nearest stars. So yeah, that was it. And then when I got a little bit older again, I read all of the books about space that was in my school library and the public library in Maitland in New South Wales. And then we moved to Melbourne when I was in year 10, and I did my work experience at the University of Melbourne in the astrophysics group. And then when I finished my week of basically lectures from the PhD students that were there, I was very sad that I still had 2.5 years of high school left to go before I could do physics at uni. So yeah, I did physics at uni. I did my master's in physics with my research in astrophysics, where I got to start to use some big telescopes for the first time, and started a PhD, had some trouble along the way, and have sort of moved into astronomy and physics education, which I really love. So yeah, get to play with the planetarium now, which is even bigger than the biggest telescope that I've used.
So using the big telescopes,
yes.
Have you used Hubble?
My supervisor has been what we call principal observer on Hubble, and I've been on programs with him and some others. I never wrote my own principal investigator proposal for Hubble, but I did write one for the Spitzer Space Telescope, which you might remember not working anymore, but it was one of the great observatories, and it was in the infrared. So the research that I was doing, we were looking at galaxies in the early universe where the light is really, really stretched out. And so even though it's ultraviolet light when the stars are emitting it, it turns into infrared by the time we see it. And so we needed to use the most infrared light we could get access to, but with high resolution still. And this is tricky because as you get to longer and longer wavelengths, the resolution gets lower and lower. So Hubble could go to near infrared, but we wanted to get a little bit further out. And so this was before the James Webb was launched, and beautiful images that it's setting out now. I could hardly have dreamed of them really when I was doing my research. But Spitzer was, so Hubble is 2 meters across, which if you put your arms out, about that big across. Spitzer is about 1 meter, if that, 90 centimeters across. They affectionately called the dustbin because it literally looked like, you know, a dustbin. But because it was in space, you actually got the equivalent of like a 10-meter telescope on the ground. So it's infrared is something that we can't do from the ground because we've got lots of water in our atmosphere that blocks or absorbs all the light getting through. So you really need a space telescope or an enormous telescope here on the ground, which is sort of what limits us. So Spitzer could do more infrared observations, and I was the first PhD student awarded time on Spitzer, and then I stopped working because I'm the only Australian PhD student awarded time on Spitzer.
That's pretty cool.
Yeah.
So when you say working on Spitzer or you're using it,
yeah,
what do you do? Like, say you write
yeah. So the way that professional telescopes work, and they all have a very similar way of doing it, is that every 6 months or every year, depending on the telescope and the funding and things, you write a proposal saying, you've got 2 pages to say, this is the science that I want to do. You've got another page or another 2 pages to say, this is why I have to use this particular telescope with this particular setup. Nothing else will do, even if it's a little bit exaggerated. And then you give them all the things you want to look at and all of the technical setup. So like, I want to look at these particular wavelengths for this amount of time because they're this faint. And so all those proposals go to a committee, and the committee reads all of the proposals, or they divvy them up, depending on how many there are. The James Webb third year call for proposals got 1,600 proposals for 1 year's worth of operation. So well and truly more time than is available on the telescope. So different experts, and the Spitzer one is based at Caltech in Los Angeles. And so they were sort of an American group there, but they rank them all basically. And you have, if you're in the top, 25% usually, you generally get all the time you ask for. And then if you're ranked a bit lower, you might get some of the time you ask for if they think you're asking for too much, or they're like, just do half of your proposal and see if it works and then come back later. Or you might just get nothing. So yes, so we wrote the proposal, me and my supervisor at Melbourne and a collaborator of ours in the Netherlands, and it was accepted, which was really awesome because we couldn't do the science literally any other way, except for waiting for the Dinosaur Space Telescope to launch.
What was the science you were doing?
Yeah, so my research was on galaxies in the early universe. So these are, as I've already mentioned, they're really far away. So the universe is expanding. The light is what we call redshifted, but it's like stretched. So it's sort of like a big rubber band stretching out. As the light gets towards us, it gets redder and redder. Everything gets fainter and fainter. It's sort of like if you hold a candle in front of your face, it's really, really hot, like our stage lights are really bright. But if they're a kilometre away, you'd barely be able to see them at all. And then as you're looking really far back into the universe, the galaxies themselves are also changing over time. So the galaxies that we see nearby, they are lots of spiral galaxies like the Milky Way, lots of elliptical galaxies because they've had 13 billion years to evolve. But we were looking into the first 500 million years of the universe. So that's when the universe was only 5% as old as it is now. And there you've only had the first stars start forming around 100 million years after the Big Bang, we think. So you've only had 400 million years for stars to start to form until you get the first like galaxies, you can call them. And so these things are really physically small. They're only about 1/10 of the diameter of the Milky Way. They have lots of really young stars though, which are really, really bright, really, really blue and ultraviolet. So they do appear quite bright, but physically they're really small and they're really far away. So trying to see them, you need infrared light because that's the light that they're emitting. You need really high resolution because they're really tiny on the sky. And you need a few other things as well. You need a lot of the sky to look at because there's just not that many of them. You're trying to find the first galaxies that form. So these are the only a few galaxies sort of dotted around the universe. You need a lot of sort of sky to look at them. And Hubble, which is what we were using to try and find them, you know, it only has a tiny, tiny field of view. So, you know, that classic, like if you put a grain of sand at arm's length, that's the amount of sky that Hubble looks over. So you want to take all these observations that you need effectively, cheaply. And so what we did was my supervisor had a big program called the Borg, which is named after Star Trek because my supervisor's a big nerd if you're watching Michele. It's the brightest of ionizing galaxies survey. And so this was designed to sort of piggyback off other Hubble surveys. So Hubble was really smartly designed because it's up in space. You do a huge amount with it sort of with your hands if something goes wrong. So you can have two instruments in the focal plane at the same time. So you can be observing one primary target, and at the same time, you can have another instrument taking data at the same time for free, essentially. Not exactly free, because you still have to get the data off the telescope, all that sort of stuff, but it's much cheaper. And this is called a parallel program. And for looking at things in the early universe, where you're just looking for these really randomly dispersed, just a few things, actually looking at random patches of the sky means that you're more likely to be able to find those things. If you just look at one big patch of the sky, we know that galaxies are clustered. So if you're lucky enough to find the beginnings of a galaxy cluster, you'll find lots of these little galaxies far away. But if you're unlucky enough to not get any of them, well, then you've just wasted a month of Hubble time, and no one likes that. So Borg was really effective. Sorry, I didn't mean to touch my mic, sorry. Really effective survey looking for galaxies in the early universe. But Hubble has a limit, and so we needed that extra infrared light to tell if there were contaminants, because every survey has contaminants, and trying to weed them all out is one of the less fun parts of astronomy. And our contaminants could have been red stars in Milky Way, so rather than things at the opposite end of the universe, could be like tiny stars in the Milky Way, or dusty galaxies about halfway across the universe. And that infrared light can help us to figure out what it is.
Did you find what you were looking for?
Hard to say.
Hard to say. Why is it hard to say?
Well, I mean, the gold standard of looking for a galaxy and figuring out how far away it is to get a spectrum. And when you get a spectrum, you can see, okay, I see a big emission from hydrogen because there's lots of gas or there's lots of stars emitting lots of hydrogen light. And that tells you how much the light has stretched out, because you can look at your laboratory and you can say, well, hydrogen's making light at this particular wavelength right in front of me, and that light is over here. So you can do some relatively simple maths to untangle it. But we couldn't take spectra of these objects. They were just too faint. There just wasn't the capability to actually do that with these really faint, tiny objects. Because if there's a bright galaxy nearby, not even nearby, even like, really distant from us still, but still brighter than the things we're looking for, that can just completely, saturate your image, and you don't get any of the data that you actually want. So it wasn't until James Webb launched back in 2021, it has an instrument on it called NIRCam, Near Infrared Camera, which is designed to take these images that I've talked about at longer and longer wavelengths, but it also has something called NIR-SPEC, Near Infrared Spectrograph, which is now designed to actually look at these objects and take spectra of them and really finally narrow down, like, okay, exactly how far away are you? And what we've been finding is that so far, the really distant galaxies that we were very sure of, that we had the best data on, we're actually finding that they are likely these really distant galaxies based on what we've observed. Still early days in terms of observations, because these are really faint. They still do take a little bit of time to get the data off, because when you're taking an image, you've got all the light smushed into one image and everything's much brighter. But when you've got a spectrum, you're taking an already really faint thing and you're taking all the light that it emits and you're splitting it all out into different wavelengths. So you've got a really, really faint spectrum. Yeah, what we're finding so far is that galaxies in the early universe are really big, are really bright, which is what we were finding with the Borg survey, which is really interesting because I didn't believe that at the time. I thought we must have some contamination problem. But there's also a bit of controversy about whether this is really what we're seeing or if it's still things like calibrating the JWST data or calibrating the JWST data or still things that are appearing to be really distant objects that are still nearby and just happen to have the same spectral sort of things in the same places that we would expect. But yeah, science is all about improving, as you go.
So James Webb's obviously got the right equipment and is large enough.
Yes.
What about something like the ELT?
Yeah, so an ELT, also the ELT, is
very fancy scientific name.
European Southern Observatory's extremely large telescope. So this is going to be a 39-meter telescope. So this is like, how many hands have we got? No more. Maybe
not enough.
Everyone all together in this room. It's enormous. I've got some friends who've been going to Chile and taking photos up at the site, and it's really astonishing. And so because the mirror is so big, it can't be made in one single piece of glass. It's made in lots of segmented pieces. And the James Webb Space Telescope also has this design so that it could fit into its little space shuttle. But 8 meters is about the biggest telescope that you can make before gravity starts to warp the shape of the telescope. And so bigger telescopes like the Keck telescope, which is 10 meters, are made of lots of segments of mirrors. And this also helps you out because the atmosphere on the Earth is what really stops us from getting that high resolution that we want for our galaxy studies in the early universe, because the galaxies that we're looking at are about, okay, let me contextualize this. 0.3 arc seconds is about the size of a galaxy. The full moon is 0.5 degrees, so that's 3,600 times bigger than one of these galaxies. So, so the best conditions I've ever seen on the Earth are about 0.6 arc seconds, which is 1/60th of the size of the full moon, basically. Still like 60 times more turbulent than what we need to see these really tiny galaxies. But with these segmented mirrors, you can actually start to move them around a little bit and start to change the shape of the mirror so that it matches the shape of the air moving around. This is called adaptive optics. And you can do adaptive optics a few ways. You can shoot out a sodium laser, and sodium is a really cool element because it has the visible light spectrum that we see with our eyes. It's got two really bright emission lines, which are both at like 589 nanometers. No one needs to know that number, but two really bright emission lines very close together in the yellow light. So they look really yellow, and if you've seen yellow streetlights, then that's because of sodium. And so you can see how that light is sort of giving you an artificial star in the sky with that big laser, and you can see how the appearance of that star is changing as the air is moving around. And then you can change your sort of secondary mirror or your primary mirror, your big one, to counteract those movements. Sort of like noise-cancelling headphones sort of give you the alternate waveform to cancel it out. Now, the thing is that with a really big telescope on Earth, you can start to get down to this really tiny resolution that you need for these galaxies, but you only do it in a very small part of your image. Even if your field of view is massive, much bigger than the James Webb Space Telescope, it's only one part of it that's going to have that really big, really high resolution, just with technical issues. Is anyone interested in this? I'm not sure. I'm going to keep talking.
I can honestly say that our demonstrator, section director, Colin,
Yes.
loves arc seconds.
So yeah, if you put a telescope in space, you have no atmosphere. All of your image is basically this really high resolution. On the ground, we can start to mitigate the atmosphere, but it gets very difficult. On the ground, you still have the problem of the near-infrared absorption. If you're on a big mountain, like in Chile, and you have in Chile, they have amazing deserts where it's very, very dry, just because of the way the Andes and the sea sort of meet. It's a really amazing place. And you get really nice air, and so you can get a little bit more of that infrared light, but still, it's not as good as going up into space.
But we can't take a 39-meter telescope up into
No,
space.
it would cost you a lot just to get the payload, like the fuel to get that all up there. And then, you don't have anyone to make it all come together up there. So like James Webb had like 1,600 or something little pins holding the sun shield in, and if one of those had failed, the whole sun shield would have just ripped apart, and that defeats the purpose of the sun shield, which is about, you can think of like a chip packet, crisp packet, which is just like foil basically.
That's the size of it. Yeah. Have we got any questions from the audience? Anyone? No? Come on. Oh, I've got 2 hands up. Oh,
No.
we've got 3 hands up. Oh, we're flying around now.
Oh no.
Oh, Dad's got a question. Steffi's dad is here tonight, guys. He didn't come for the interview. He came to look at the telescopes.
My daughter's talking. I want to ask you, Stephanie.
Hold it up closer.
I want to ask you, Stephanie. So we read a lot in the media about artificial intelligence and how it's going to change our lives. How do you think artificial intelligence is going to change your life as an astrophysicist?
Yeah, and actually a friend of the ASV, Sarah Webb, works on AI in physics. So one of the things that we do a lot, I don't do it because I was looking at 20 to 30 galaxies, but if you've got a lot of data, you want some way of analyzing it all really quickly, is using something called machine learning, where you give a computer code some data that you have classified, and it can go through some other data and it can start to use that classification that you've done and some other things that you set to work out what's going on here. And so one of the classic ways of doing it is trying to work out, well, what is a star in the Milky Way and what is a quasar, or a supermassive black hole at the center of a galaxy? Because when we look at them with our own, not with our own eyes, but with telescopes, they look very similar. Sorry. But they do have unique, what we call spectral features. A star is but a star is a burning ball of gas, and mostly hydrogen, some other little bits and pieces as well that give it these uniquenesses. But we generally know what the spectrum of a star is going to be like. The supermassive black hole is lots and lots of gas whirling really fast around the black hole, getting really hot, making lots of light that way, making lots of radio light as well, making lots of X-rays, so all sorts of different light that the star is not expected to look at. So trying to give a computer ways to work out, okay, it's got this property, it's got this property, it's got this property, this means it's a star or it's a quasar. And that's something that they've done with the Sky Mapper telescope survey that was done in the last decade over at Siding Spring. As they were looking for stars in one of their big surveys, trying to map all the southern sky. But of course, when you map the southern sky, you also get all of the other stuff that's in the sky, and finding all the black holes that you can is really important as well.
So they use that same technology trying to hunt for supernovas, don't they?
Yes.
Getting the AI to go,
Yes.
1 image, 2 images, subtract, there's the difference.
Yes.
And then if you see the difference, then you know something's happened in that area of the sky.
Yeah, exactly. And so it's a technique that is dependent on what you put into it. And so if you give it a bunch of bad training data, it's called, it's going to come up with bad results. So the human still needs to be looking at it being like, does this make sense? But definitely something that as our computers get more and more efficient and these codes get better at training and starting to train themselves, I'm like, oh, I've noticed this other correlation that you didn't tell me about, but maybe that will help us out. That sort of thing can really help to speed up going through data. And like the amount of data that we're expecting to get from telescopes, so the Square Kilometre Array, which we might have heard about in Western Australia and in South Africa, the Murchison Wide Field Array is like hundreds of telescopes essentially all working together at the same time. So every time you're taking an image, you've got all these hundreds of different telescopes taking data at the same time. You get like each image is like, I don't know, a terabyte or something. And, the people who look at it, they don't care about the stars or the galaxies, and some of them do, of course. But if you're looking for like the hydrogen in the early universe to see when all of the stars were being made, you don't care about the gas from these black holes basically spinning around, which also emits radio light. So you've got a terabyte of data. All you want to know is, am I seeing the signal of that hydrogen? And then I can throw it out if it doesn't have it. And so being able to work through that sort of thing really quickly. And if you get 100 images a night or something, you're quickly making up to, I think it's petabytes of data they expect every year.
Trying to sift through that is near impossible. Well, it is impossible for us.
Yeah, people can't do it. Grad students can't do it.
Got a couple more questions over there.
The adaptive mirrors on the telescope in Chile, is that the same as on the James Webb?
So James Webb doesn't
Is that
need that sort of thing because you're trying to react to how the atmosphere is changing on a really short time scale. So James Webb doesn't have a telescope, but it doesn't have an atmosphere.
It did it initially for the focusing purposes.
Yes, exactly same process to get the best focus. And the Keck telescope as well does the same thing. Every time you go, not every time you take any observation, but every night, you've got 36 different mirrors all working together. So you have to run basically a focusing routine, which will move the mirrors slightly and make the, like a standard light appear the best focus. And so exactly what you've said is how it's focused in the first place.
So adjusting to the atmosphere, how quick can it perform that?
You have to do this on like less than a second sort of time scales. Like if you think about like the wind, if you're standing outside, 1 second you could be getting wind from this side and the next second it could be coming from this way. And so it's a really turbulent thing to try and look for.
That takes some engineering.
Yes, absolutely. And there's a group at ANU up in Canberra, and they work on adaptive optics systems that have gone out to telescopes, I think in Chile. But they're very, very talented engineers to make it work. Yeah.
All right, thanks.
Yeah.
Next question.
You said earlier that you're studying galaxies which are half the size of the Milky Way.
Yes.
Was that the average size of the galaxy at the start of the, just after the Big Bang?
Yeah, that's a good question. So when we had the Big Bang, and then we have the universe getting bigger and bigger, and so it's getting bigger and bigger, but the amount of stuff inside is staying constant, so the temperature is decreasing. And to make stars, you need the gas to actually be quite cold. So it took about 50 to 100 million years for the gas to be able to cool down enough that the first stars could start to form. And the first stars are thought to be, it depends on who you ask. It depends on which simulations they've run, because we haven't seen any of the first stars yet. But thought to be between like 30 times the mass of our sun up to, usually 100 is sort of the upper limit, but some people go up to, thousands. At that point, you're actually just taking all the gas in the cloud and just dumping it into a black hole at the center. It's called a direct collapse black hole. But 100 solar mass, 100 times the mass of our sun star is like out to the orbit of Jupiter or like Mars-ish, somewhere around there. So quite big stars, but still much, much less than the size of a galaxy itself. So we think that we would have formed the first stars, and they formed where this gas that was sort of just after the Big Bang in that first 100 million years or so, it was a little bit clumpy from, the just dark matter, basically, clumping it up a little bit. And so you have, the most massive bits start to collapse first, make these really big stars, and then you would have gotten other smaller stars likely. And so you start off with star clusters, sort of similar to the open clusters that we see today, but the stars would have been much bigger and brighter, and they would have had more ultraviolet light as well. And that ultraviolet light can just sort of blow out all of the gas around it, so that sort of naturally stops the star forming, which is a shame because it'd be really cool to have really big stars, but I don't control that. So you start off with star clusters, basically. And over time, you build up more and more of them start to collect together. You might end up with what would look more similar to like a globular cluster today, really tightly packed bundle of stars. But the first galaxies would have been similar to our irregular galaxies that we see today. So not really much structure, really no spiral arms. We don't see spiral arms forming until about, what's the furthest back? This was work done by a friend of mine who was at Swinburne and is no longer, but about 2 billion years after the Big Bang is when the first spiral arms start to emerge. Just because it takes a long time for these galaxies to sort of settle down. You definitely don't see any elliptical galaxies unless you've just got sort of like something that forms as an elliptical type of galaxy. So we're really like, if you think of like the Large and the Small Magellanic Cloud sort of galaxies, that's what we're looking at. Those are the biggest galaxies in the early universe. So really different than what we observe today. So how we went from there to here is one of the questions that we want to answer. Stars are different, the amount of gas is different, the type of gas is different, there's different chemicals in it. But if we don't have a clear view of what's happening in the early universe to start with, we really can't answer that question. So up until James Webb, we're really just sort of trying to
Guess.
not guess, but it's sort of like the old movies with the Vaseline on the lens, like you're just sort of waiting for someone to come along and rub it off with $1 billion telescope.
So what you're saying is we don't know why they formed that way. Which one is that? It's us, Lee. Well, there we go. Sorry. We don't know why they were forming that way and why they form the way they do now yet.
We have a pretty good idea of how the galaxies got to where we are now. We can simulate galaxies from very early in the universe and look at how galaxies evolve with dark matter and the stars and things that we observe, like from about 1 billion years on. So about 1 billion years after the Big Bang to now, it's reasonably easy to see these galaxies. You're not getting really into the infrared yet. You can still use our standard optical telescopes to do this. I say this in, this is work that was developed in the, 1990s, nearly 2000s. So by the time I started graduate school, this was like old stuff, but, still people around who, that's still like, really far away from their perspective. And, so like what sorts of galaxies there were, what sorts of stars there were, still a bit of a mystery. And all of the data that we're getting with the James Webb Space Telescope is helping to sort that all out. I think it's going to be another 5 years or so before we can really get a big amount of data to actually analyze it all as a big chunk, rather than just one group saying, okay, I've taken a spectrum of this particular galaxy, this is what it looks like. Another group from different countries saying, I've observed this other galaxy, this is what I find. Those observations are really important because, even like one of them can be like, oh, this is really weird. This is not what we were expecting to see. Maybe there's some new physics there, which everyone would love to have. If it had been discovered, you would hear about it. We can't keep secrets. But once you can start to get all of these discoveries together and actually start to analyze them as a big set, that's when we can start to make sort of connections between, okay, well, what are we seeing in all these different wavelengths for all of these different galaxies? What do we think is happening in the early universe, which we're not up to yet, just because of time.
NASA's very good at keeping secrets, all right? I mean, we didn't land on the moon, remember? We kept that a secret, what?
I won't engage.
You won't engage?
No.
I want to
I've got so many moons on me.
I know you're mooning the audience. I've seen a comment
Yes.
on our stream that I'm going to come. I'm just keeping an eye on the time. We've been chatting for nearly 40 minutes.
Oh.
I'm quite enjoying this new format of presentation. I think it's a little bit more personal than just being spoken to about a topic. But you mentioned the planetarium,
Yes.
and one of the viewers watching has noted that they believe it would be amazing if there was a travelling planetarium in a van type set up for country kids to access.
There is, what is it called? It is called,
Googling.
and I have a picture on my phone. I don't think they've got a planetarium, but other universities do have them around.
And you have telescopes in schools as well.
Telescopes in schools, which is at a few schools around Melbourne at the moment, not as many as it used to be, but where are we? There we go. It is called Science Discovery Dome.
Science Discovery Dome.
Yes.
Who does that? Is that the Discovery Centre?
I'm not sure. Science Discovery Dome, I think they do school visits with a planetarium.
There we go.
But we are hopefully looking at getting one at Melbourne Uni that I would like to monopolise for doing lectures with undergrads, where rather than a person standing in front of a whiteboard talking, you can actually go to the thing that you're looking at and really see it sort of actually happening in front of you. I don't no one will let me do that just yet, but definitely something that would be really cool. So a friend of mine at VSEC, Emma Barnett, does a program looking at taking telescopes to schools, and this is part of the Victorian government's knowledge enrichment series, where it's meant to sort of challenge high-performing students out in the country who may not get opportunities to do things like this. But yeah, I think definitely a roving planetarium is my dream job.
That's what you said there about highly intelligent children who don't get that exposure and opportunity. That's one thing that we noticed with the going out to sea like
Yes.
the young kids that were coming along that just don't get the exposure that the kids in the city get, which is why it's important to go to places like Hamilton and do what we're doing.
Yeah,
We're doing out there as
absolutely.
well. So I like the idea of if we can work it for next year for Sea Lake, if you'd like to, we can get you we can work out get a mobile planetarium up there. You can do some daytime
It would be
things with the kids.
absolutely yes.
We had an entire class from the school coming camp the whole weekend.
So good. Yes.
That'd be so good.
It would be awesome. So like Harold the giraffe, but school band, but with stars instead.
I have a question for you.
Yes.
Starting from the Big Bang,
Yes.
holding the periodical table in front of you after hydrogen and helium,
Yes.
how long did it take to fill the chart with all the elements we've seen today?
Awesome question. I have a poster with this on my desk at uni. Let me visualize it. So hydrogen, helium. So hydrogen beginning.
Yep.
And depending on how you define hydrogen, because generally it was not hydrogen as a proton and electron, but it was the proton by itself, the electron by itself for a long time. Hydrogen, helium, lithium, beryllium, boron are sort of the unstable steps to getting the rest of the elements. And so it was actually Fred Hoyle, who was a scientist, coined the term the Big Bang, but didn't actually believe in the idea. He called it the Big Bang so that, people would find it silly and they wouldn't take it seriously. But he actually worked out what we call nucleosynthesis to get helium. So helium-3, 2 protons, 1 neutron, colliding together to eventually make carbon. And so carbon would have been very, very, very tiny amounts just after the Big Bang. Anything beyond that, just too high energy for what was there. Because just after the Big Bang, you've got the amount of energy that is there, but there's no way to jump up and get more energy apart from atoms smashing into each other. And if they're not smashing into each other fast enough, you're out of luck. So it's not until the first stars started to form. So we have, after what we call the cosmic micro background is released, so the universe is getting bigger and bigger, it's getting cooler and cooler, and those protons and electrons that were separate, they start to form together again. And the way that I usually describe it is when you go to a party, and I'm in my 30s now, so I don't get invited to parties anymore. But when I was younger, you go to a party, you turn up there at 8 o'clock, you got your bottle of wine, you want to put your bottle of wine on the drinks table, grab some snacks. Everyone is there though. It takes you a while to make your way through the crowd to get to the drinks table. A bit later on though, it gets to about 10 o'clock, everyone started to sit down, they're having their chats. My dad doesn't like hearing that I went to parties. Everyone's sitting down, it's much easier to make your way straight to the snack table and back. And so this is sort of like the early universe. You know, everything's really high energy, everything's moving around, but it all cools down and it's much easier to move around. And so once that light was released, you've got lots of hydrogen, a little bit of helium, about 25%, and nothing else really, tiny, tiny amounts of anything else. The hydrogen is still making light. It's not light that we can see. It's very, very faint light from the electron spin flip, which is a quantum mechanics thing where the proton has a spin, the electron has a spin. It's slightly more energetically favorable for their spins to, I think, match up. But sometimes they start off unmatched. And so once every like 20 billion years or something, they will change and they'll let out a little bit of light. It's radio light, 21 centimeter line. And if you've got, 20 billion hydrogen particles, you'll see one every year. And if you've got 20 billion particles or, however, you'll see like a reasonable signal of this happening. But it's not until the first stars started to form that you start to actually burn those heavier elements again. So, hydrogen, helium at the beginning, a little bit of lithium, boron, beryllium, carbon, and then not till, that first 50 to 100 years, million years, when you get the first stars. First stars are going to be really, really big and bright. They're not going to burn for very long, maybe like a million years or so. So you can actually get quite a few generations of stars from the first stars to these galaxies that we were looking for with Hubble and now JWST. But they are going to make lots of carbon, lots of oxygen, lots of nitrogen, and lots of neon, but not so much fluorine. Oh, gosh, where's my periodic table? The odd elements are harder to make. They're less energetically favorable. So you get this, like if you plot the atomic number.
So that they come along and then there's gaps and then.
Yeah, if you plot the atomic number versus the abundance, you get like hydrogen up the top, helium, down here for boron, beryllium, and then carbon up here, down for 7. Oh God, someone help me. Sorry?
Nitrogen?
Nitrogen, yeah. And then oxygen high, and then fluorine low, and then neon high, and then like, the other like half the table is different again, but yeah. So, and actually people look at these what we call abundances of elements in stars and gas to see like how many generations of stars there have been, what sorts of supernovae have happened to make the different chemicals in this, because supernovae that occur from stars that are really, really big, they make different elements than supernovae from white dwarf stars, which are what we call type 1a supernovae. And you might hear these about standard candles and dark energy and things, but because those are originally white dwarfs, which are the cause of stars, they're actually more carbon and oxygen like originally from the initial star, whereas a massive star has a huge amount of hydrogen, not in its core anymore because that's all been burnt up, and in the outer atmosphere a lot of hydrogen. And so you get different things being made in these different processes from different types of supernovae.
So now that we've worked that out,
I don't think that was a very...
how long though? Like we've got part of the way through, and we got to start the galaxies being formed, which is sort of we're saying what's about 500 billion years. Yeah. But we're still not full. The hydrogen table, sorry, the periodic table at that point is not.
Yeah.
All the main elements aren't there.
It's so all of the elements up to iron and nickel are going to be made in these stars.
Yep.
That eventually become supernovae. And then you get different elements being formed, like the ones that are sort of down at those tips, you still have that element there, it's just a lot less abundant. Yeah, exactly.
So we're basically saying 500 billion years.
500 million
500
years
million
ish. Well, I mean, even like 50 million to 100 million years, you're going to have the first really massive stars start to burn through all of this stuff. The supernovae that come from white dwarfs, they don't happen till a lot later on in the universe.
Yep.
So it takes you maybe, our sun is going to last for 10 billion years. A star that is maybe twice as massive as our sun will last for maybe 3 billion years. And 3 billion years is still like 30% of the universe so far. So,
Still pretty long.
Still pretty long. So, and then of course you get to the, all the elements that are made by humans in labs, they didn't occur until 13 billion years after the Big Bang. So it's taken a while to, and who knows which elements are still out there that we haven't gotten to yet.
I'm going to go back to my day job now. That was, hopefully, Gunnar, hopefully we've answered your question. Well, sorry, not we, because I didn't. Hopefully, Steffi has answered your question as much as she can, that's for sure. I'm going to come back again to the planetarium stuff because I know how cool that part of the job is. I know how much you enjoy that part of your job. What exactly do you do at the planetarium?
Yeah. So my job, I am a learning facilitator. I do shows in the planetarium. Mostly this last few months has been on the weekends, and then for the public, so families with kids or adults, looking for something fun to do on the weekends. And that is a 45-minute show. So there's a half-hour movie and then 15 minutes of me talking about the sky. Usually start with planets. We'll start with the moon if it's around, but you can only see the moon in the early evening quarter of the month, so it's not super likely. Start with planets. So at the moment we've got Jupiter and Saturn being beautiful in the early evening. It also changes over the year. Looking at the constellations. So at the moment, Scorpius is setting in the early evening, but still lovely and bright. And Sagittarius as well can sort of see suburban skies here in Melbourne. And then, in a few months we'll have Orion, lovely and bright up in the sky. And I love to see Orion because it reminds me that summer is coming. So always very excited when that's happening. Talking about some of our First Peoples, their Indigenous constellations as well. So we've got lots of information and lots of animations and pictures about Burong constellations in the planetarium. And those of you who went to Sea Lake might have heard a little bit about the Burong constellations because they were in the area around Lake Tyrrell. So yeah, another reason I'm so sad that I missed it, but anyway. So yeah, and then go out to the galaxy and look at, okay, we see the galaxy from the ground, what does it look like from the outside? And, then ending with flying through the galaxies, which is always the best bit, I think, as a galaxy.
That can take you right back to the start.
Yep,
right?
exactly. So sometimes we do longer shows where you start from the Earth and you go all the way out from, through the solar system and basically increasing your order of magnitude of your distance every time. So solar system, nearby stars, Milky Way, nearby galaxies. We have the 2DF survey, which is the 2DF, 2 degree field galaxy redshift survey, which was done by Australian scientists in the 1990s and was one of the first big surveys of galaxies. So I mentioned that I have 20 or 30 galaxies, but this is, thousands, tens of thousands of galaxies from the Anglo-Stellian telescope. And then we bring up Sloan data as well, and that's, a million galaxies. And I was mentioning to some friends today at the planetarium that the Euclid Space Telescope, which just released its first images today, it is going to have 1 billion galaxies. So if you've ever seen the Sloan galaxies all out in space, if you think of that density, 1,000 times more dense, that's how many galaxies Euclid is trying to find. So yeah, I would love to just keep shoving more and more galaxies into the planetarium. I've got friends who work on radio galaxies in Perth and in Sydney on visible galaxies and our work on early galaxies and just putting it all together and really doing rather than starting from the Earth, start from the Big Bang,
Stuff a bit,
And
go the other way.
go the other way, and end up at Earth and be like, all that stuff had to happen for us to end up here. Isn't that cool? That's my dream. Please give me lots of money to make this.
Oh, you heard it here first. Everyone has to go and spend money at the planetarium and science.
No, I need a grant.
Oh, you need a grant. Okay, well, let's get a
Haven't you
let's
worked
get a
in
grant
academia
then.
before?
So I have seen behind the scenes of the
Yes.
planetarium. It's very cool. A lot of computers.
Yes.
Because there's a lot of programming that needs to be
There's-
done
yes,
to make those
heaps.
videos that we all watch.
Yeah, and in the planetarium there are 6 projectors as well. So there's, I think, 2 computers working each projector, so 12 computers, and they all talk to a main computer, which talks to the one that we have all of our software set up on. And so if one of them goes out, the whole thing starts to go out of whack, which doesn't happen very often, fortunately, and we have people whose sole job is to keep that working. But yeah, it's honestly like walking around the back of the planetarium and walking around like the catwalk of a telescope, like a big telescope. Like, honestly, very similar experiences.
All right, I'm going to close it out with one last
Sure.
question, just looking at the time.
Yes.
Hi, Steffi. That was my fault. He actually wrote Steffi. Thanks for another amazing talk. We were fortunate to hear some amazing talks on the weekend.
Yes.
If you could have an amazing discovery with your name on it, what would that be?
So one of the things people used to ask me when I was doing more like observing was, if you find a galaxy, do you get to name it? And I would say yes, but you have to name it really boring things. So the galaxies that I found are named after their coordinates on the sky, their right ascension and declination, and a catalogue number. But some people have bucked the trend and named their things. There's one which is a big ball of really highly energetic hydrogen gas, whether it's stars or things like that. And it's called CR7. And that's after Cristiano Ronaldo 7. Literally in the paper. So I looked at galaxies and we tried to find the biggest and brightest galaxies in the early universe, so the ones that were easiest to find, really. And I really wish that I had given them more interesting names now, rather than 1169 plus 04 something. Yeah.
All right, well, thank you very much for
Thank you.
spending time with us and sharing your knowledge with the people who are here and the viewers at home as well. It was a bit of a different style tonight. I think it actually worked quite well.
I hope so.
And thank you, Susan, for coming along. And for those who don't know, Steffi is actually the ASVs Ambassador. She's essentially our #1 ticket holder. Yeah, that's what
Ticket holder. I thought you meant draw. And I was like, oh no.
You're our #1 ticket holder. You are the ASV Ambassador, and you do a lot of work for women in STEM and outreach for kids as well, which is wonderful and something we're trying to get into a lot more as well. But again, thank you for everyone watching. Thank you, Steph, for coming. Tickets for the Christmas barbecue will go on sale for the public tomorrow and for members tomorrow. For members, you will get an email with the member link, and it'll be on our members forums as well. So keep an eye on for that. Eye out for that. But until next time, blue skies.